Okay, so today we're honored to have Professor Kim Vandiver, who's a professor of mechanical engineering here at MIT, was in the ocean engineering department. He's also the dean for undergraduate research at MIT, so Europe and all that. He also teaches 2003 in last fall and I guess again this coming fall. So let's welcome Professor Vandiver to 1803. So we've been studying these equations. Let me bring Professor Vandiver up to speed a little bit with what we've been doing for a long time now. We've been studying these equations, which getting to know them pretty well. So there's a spring system maybe, and it's being affected by some external force, which I've called Fx'd. And we are interested, for example, in the case when this is 0, so the homogeneous case, when Fx is 0, and then it's just this equation. This is surely too simple to be of any use in a real engineering application, though. Is not right?
I use this equation all the time. In fact, my particular specialty is structural dynamics. And this is the oscillator equation. And it is, if you understand it well, it helps you understand everything in nature that vibrates. And just about everything vibrates. It'll make noise, it vibrates. Musical instruments, pianos, stringed instruments, horns, they all are based on vibration of one kind or another. In this equation, if you understand it, you can understand a lot about it. Now, why am I here? Because in the first, how many of you might be mechanical engineers? Well, you might be taking 2003 in the fall. In the first lecture, when I gave it this year, and I put this equation up, and I said, now, of course, you all saw this in 1803, right? And I got these dumb expressions on their face saying, huh? So I'm here to tell you, I really want, when you come in, I say, you've seen this before, you're going to say, right on, I remember. Okay, let's go. So how might you do, what's the response to this homogeneous equation look like to initial conditions?
Okay, so we, in this class anyway, we tried to address solutions of this by looking at the characteristic polynomial. So I'll write that out. It's ms squared plus bs plus k. And solutions correspond to roots of this thing. So let's find the roots of it. I'll factor this in some way. So I'm going to factor out the m, and I get s squared plus b over m s plus k over m. And then I'll complete the square to see what the roots look like. So I get s plus b over 2m, quantity squared, plus, and then there's the k over m from this, and then I want to subtract the b over 2m squared that comes when you square that part. So same thing. And so the roots, well, now the roots depend upon whether this quantity is positive or negative. And so we should think about that case. If k over m is greater than b over 2m squared, this is positive. So when I put this on the other side, it becomes a negative. And when I take the square root to get rid of the square, I'm going to get an imaginary root. Imaginary root. And my word for this is underdamped. Is that an engineering term too?
Yep. So systems that are underdamped are the only ones that vibrate. And here's your giant piano string. It vibrates. This is surely underdamped. And if I'm interested in vibration, I'm only interested in systems that vibrate. And if they're overdamped, they just don't do much of interest. So let's talk today about things that are underdamped.
All right. So if it's underdamped and that's true, then I can work out what the roots are. The roots are, there's a real part, minus b over 2m, and then plus or minus an imaginary part, which I can write I times omega d. And omega d is the square root of that stuff, the square root of k over m minus b over 2m quantity squared. And so those are the roots, and that gives rise to this kind of solution to the homogeneous equation. So there's some amplitude, and then there's an exponential decay term, bt over 2m, e to the minus bt over 2m. And then there's this vibratory term, cosine omega dt minus phi. So this is the way we handle this. This is the general solution to this underdamped homogeneous equation. So does this look familiar?
Well, it's familiar, but now I'm beginning to realize why my students have looked at me and said, huh? Because I tend to use slightly different notation. So over here, and I think the simplest way to show you my notation, and a notation that's pretty common to engineering, is to take note of the fact that when there's no damping, you get the undamped natural frequency.
This is notation we've used too, omega n.
Omega sub n, and that's just the square root of k over m. Now, if I take this expression for the damped natural frequency and just factor out of it this k over m expressed as omega n, it will look like omega n times the square root of 1 minus b over 2 omega n m quantity squared. And I have a name for this. This is also omega n times the square root of 1 minus zeta squared. And this zeta, then, is this quantity, and it's known as the damping ratio. When this number is greater than or equal to 1, then that's when you don't get vibration. It's overdamped. So when this number is 1 is that critical crossing point where you go from overdamped to underdamped.
And
so we're only interested for today's lecture in when this number is less than 1.
So zeta is 1 is critical damping when there's only one repeated root.
Right. So I tend to use expressions like omega n and and the damped natural frequency is omega n times 1 minus zeta squared, and then I'll express solutions in the instead of b over 2m, I do minus zeta omega n.
So let's do that. Let's try to make that substitution and express the equation and solutions in terms of this zeta. So the equation, I'm going to divide through by m in the equation. So I get x double dot plus b over m. Let's see. Where is your definition of the damping ratio here?
Well, it's basically, I just said it's that quantity.
It's that. So let me re-express what this
b
said.
over 2 omega n m.
B over 2m is omega n zeta.
Right.
That's the stuff inside the square root is zeta. So b over 2m is omega n zeta. b over 2m is what shows up in the middle of the differential equation when I divide through by m. So the middle term is, so b over m is what shows up there. So the middle term is twice zeta omega n x dot, and then there's omega n squared at the end. And so that's the same equation we've been looking at, but written out in terms of the natural frequency and this damping constant. And now you can see if zeta is equal to 1, this is critically damped. So here's the equation. What does the solution look like? Let me rewrite the solution that we had up there. It's it's a e to the, hard to get all these. There, that solution. If I write that out in terms of zeta here, b over 2m is omega zeta, and that's just what shows up there. So I get omega n zeta t times the cosine of omega d t minus phi. So there's a way of writing the general homogeneous solution out in terms of the damping constant. By the way, what are the units of this zeta thing? I mean, omega n has units per radians per second. It's circular frequency. It's radians per second. What about zeta?
Well, I just take a look here. This t has units of time. Omega n has units of 1 over time. They cancel. So what's left? This exponent has to be dimensionless. So what's this fellow here is dimensionless.
Dimensionless.
The
So
ratio.
so you
This
mean
has units of time. That's 1 over time. They cancel. You're left with no units. And this also has no units.
so you mean if I switched units from feet and seconds to meters and hours, the zeta wouldn't change? Omega n would certainly change, but zeta wouldn't change?
Right. So as long as you're consistent up here, newtons per meter per second and kilograms, that'll work out. Or you can do it in English units.
So this is this amazing thing. It's a ratio. It doesn't depend upon units at all. It's an invariant of the system that you're looking at. And it tells you whether it's damped or underdamped. So maybe we can actually measure these things in a real system. Shall we? Let's see. What do we do?
Let's find this. We've got an oscillator. Why don't we hang it from our hook here and measure the natural...
we have a hook here. That's right.
Let's measure the natural frequency.
Okay.
And I'm not checked out in this room yet, so...
That's a good one.
That's not the right one,
Try the
though.
other one, too.
Okay, here we go.
Notice something, stop it here. Notice something before this disappears, that when zeta is small, when there's not a lot of damping, then omega d, way over here, is very close to omega n. Look, if zeta is small, zeta squared is very small. If zeta is 0.1, this is like 0.01. You get 0.99, and the square root of that is even closer to 1.
All right,
Yeah,
I give up.
No.
There we go.
There's a training course for this. It's 2 weeks long. Now you're hooked.
Leave it. All right. That's good. All right. So...
Shall we put this up? I'm not sure that well, we'll see how well this
I think this
swings.
one. Magnets here if you want to try it. This is a... Okay. Yeah. Let's get that. They have parallax, so let's do it about like that, I think. All right. So if we give... we should have let that stay hooked, I think. I'll do this. So if we give this an initial deflection downward, like down by this line, and let go, it'll bob up and down. I need to do it straight. I'll let you hold that. I've got a stopwatch. Let's get the natural period of this thing first. So I'll say start when it gets back down to here, and then you're going to help me count periods. We're going to go to 10. Start. 1, 2. All right.
By the way, were they all the same? Is the period the same as it goes along, or does it slow down? It's always the same.
14.2 seconds. So that was the length of time for 10 of them. So the period, which I write tau, and I think Professor Miller writes p, is then 14.2 divided by 10, or that's 1.42 seconds per cycle. And if you invert that, 1 over p, you get the damped natural frequency in hertz. So 1 over
About 0.7.
1.42 inverse is about
0.7.
0.7 hertz.
And we've always been talking about, so that's cycles per second. We've always been talking about circular frequency, which is radians per second. So here's the relationship. 2 pi radians in a circle. So we should multiply this by 6 point something, and you'll get
4.3 or so radians per
about
second.
4.3 radians per second. So we figured out omega d by observation, and omega d is pretty close to omega n, which appears in the equation. So we're working out what the constants are in this equation that control this spring.
So if you're a vibration engineer and you really want to know what damping is, and you'd like to be able to estimate it quickly, you see a problem, You want to get a quick estimate of the damping of a system, and I have a simple little formula for doing that.
All right, then we can measure it out.
See if we can measure it and then figure out where this comes from. So I say that the damping ratio is 0.11 divided by the number of cycles it takes to decay by 50%.
Well, let's measure that. Let's measure this number first before we get into why this is true.
So what I'm saying is if I pull this down...
Maybe we can actually pull it twice this distance down.
Ah, okay, we can try that. This is rubber bands. Rubber bands actually turn out to be kind of nonlinear. But let's hope that within first approximation here. So it's going to bob up and down like that, and as it decays, when it gets down to this amplitude, I want you to count how many cycles it takes to go from being twice this amplitude back to this. So let's give it a shot.
So this N50 is the number of cycles till it halves the amplitude.
Got that? All right. 1, 2, 3, 4. About there.
What do you
Say
think?
about 4 cycles? It started here, and you only could get that far after 4 cycles. So try it out.
So it's about 0.20.
About 2.5, say 2.6, yeah. Zeta, and that's, an engineer would say that's 2.5% damping, 2.5% of critical damping. And quick way to measure it.
So where did this 0.11 come from? So let me see if we can work this out mathematically, where that 0.11 came from. Don't pay any attention to this black rope.
We don't usually have these distractions like this during lectures, do we?
So the first thing I want to do is graph this damped response that we have here. And to do that, I'm going to first of all draw the exponential part. This is the exponential decay and the negative of that. So that's the curve A, e to the minus, what was my equation here? Oh my, it's lost now.
Zeta omega.
Thank you. Zeta
Omega n.
omega n
T.
T times, and then that's the exponential decay. And then inside of that, the solution bounces up and down according to the cosine. It gets multiplied by a delayed cosine. I don't want to control what the delay is, but that's what it looks like. And as you pointed out, the place where it becomes 0 is, this is the half period, because they're multiplying by the cosine of omega d times minus a phase lag. But what we were measuring was the bottoms or the tops. So what happens? Where are these maxima? There's a maximum, and there's a maximum. Actually, there's a maximum. So how often do they appear? How often do they come by? This is a question we haven't really addressed. Notice when the cosine is 1, you're meeting this exponential. You're multiplying that exponential by 1. When the cosine is 1, you're right there. You're tangent to the decaying exponential, and it happens again here. But that's not a maximum, because this exponential decay is slanted. So the maxima don't quite occur when cosine equals 1. Where do they occur? Well, I want to just think about what happens when I take the derivative of this function. I'm going to draw the function again here, cosine of omega d t. Maybe I won't worry about the phase lag. How often, where does that function become 0? So just think about this for a minute. I'm going to calculate the derivative by using the product rule. There are 2 parts to it. Whenever I differentiate an exponential, I get the same exponential back again times a constant. So this is going to be a times e to the minus zeta omega nt. And then what are we going to get? Well, in the product rule, if I differentiate this part, I'm going to get cosine times this bit. When I take this times the derivative of this, I'm going to get same exponential times sine. Both terms involve this exponential and a sinusoidal function of circular frequency omega d. And we know that when you take a linear combination of sinusoidal functions of a fixed circular frequency, you just get another thing of the same type. So without actually doing the calculation, you know that x dot is this exponential times some some sinusoidal function of circular frequency omega d. We could work out exactly what it is, but I don't need to know it. That's all I need to know, because that tells me when x dot is how often x dot is equal to 0. How often is a sinusoidal function of circular frequency omega d equal to 0? These zeros are spaced out by p over 2, right? Every half period, that sinusoidal function becomes 0. I can't say exactly where, but every half period it becomes 0. And the maxima occur spaced out by a spacing of p. Maxima are p seconds apart. Okay, so even though they don't occur where there's contact made with that purple curve, they still occur at spaced out at a distance of p from each other. So we can use that. That's what we were working with there. In the course of adding p units of time, the amplitude in p units of time, p seconds, the amplitude, that is the purple curve there, is multiplied by, well, by e to the minus, where is it, zeta omega n times p. That's what exponential functions do. It multiplies by this every time you increase time by p units. So let's work this out now. We did that experiment. We let some number n sub 50 cycles go by. And so what we find is that 1/2, the amplitude is multiplied by 1/2 after n sub 50 cycles. So minus zeta omega n p, and that's done n sub 50% times. So that's the meaning. That's how this plays into things. The amplitude gets multiplied by this factor after n sub 50 cycles. So let's try to calculate this out now and see if we can find zeta from this number. That's what Professor Vandiver was doing here, except there's that mysterious 0.11. So let's get rid of the exponential by taking the natural logarithm. This is minus the natural logarithm of 2, and that cancels with this minus sign. So I get zeta omega n p times this number that I'll n50. Okay, now what's p? P is 2 pi over omega d. And omega d is omega n times the square root of 1 minus zeta squared. That's how it showed up at the very beginning. Maybe it's gone from the blackboards now. So if I put that in here, and in fact, I think at this point I will make the approximation that when zeta is small, then 1 minus zeta squared is very close to 1. And so this is very close to 2 pi divided by omega n. In other words, you can replace omega d by omega n in that calculation. So what happens here? I've got p. I'm going to put this formula in for p. So I have zeta omega n 2 pi divided by omega n times n50. Cancellation happens. These cancel. And that lets me compute what zeta is in terms of this number of cycles. And what I get is the natural logarithm of 2 divided by 2 pi, and all that over n50. So there's an estimate for what zeta is in terms of the number of cycles it takes until you reach half amplitude. And it has this mysterious numerator in it. Does somebody have a calculator handy? Can we see what natural log of 2 divided by 2 pi is? Nobody has a calculator just right in their hands at this very moment?
0.11 and some change.
So this number is the mysterious
0.1103.
So that's where this 0.11, this engineering rule of thumb, comes from. If you want to calculate the damping constant from counting, the way to do it is count the number of cycles till you reach half amplitude and take 0.10 over it. Great. Terrific.
So I said before that this simple oscillator equation applies to much more complicated things. I'd like to know how much damping, for example, this...
Let's get rid of this thing.
Bring that down. Would you want to... We can try using this. About like that. So the string, when it vibrates, it's like a guitar string or piano string. In its first mode of vibration, looks like half a sine wave. And that's when you pluck your guitar string, that's the dominant sound you hear. But it has other natural frequencies as well. There's one. So it has many modes and many different frequencies. But any pure vibration at one of those frequencies, the vibration behaves exactly as the simple oscillator equation. So we can use the conclusions for the simple oscillator equation to characterize the things like the damping. So let's measure the damping of this string. We do the same thing, pull it down. I want to put my little stopper here so it lasts.
So this spring is a much more complicated system than the simple spring system we had. It's got infinitely many degrees of freedom. It's controlled by a PDE, but nevertheless, apparently its properties can be understood using the simple spring system we've just been talking about.
So let's count roughly how many cycles it takes for this to decay 50%. So I've tried to make this line up with its mean position. Pull it down to here, it's going to vibrate, and when it gets back to here, tell me how many cycles. 1, 2, 3, 4, 5. About 5? What's the damping?
Comes out about the same.
0.11 divided by 5, 0.01 times 2.
So amazing. So this mass system and this string have something in common. They're about 0.25 or so % damped.
Right. So lots of things vibrate like that. You can estimate their damping by doing simple experiments if you can make them vibrate one frequency at a time, one mode at a time. Okay. Hey, we want to do some other stuff before we run out of time.
Yeah.
Time's flying.
So we've been talking about unforced vibrations now. Do you have some forcing to happen here? So we could use the camera now. We have a document camera set up. What do we have here, Professor Vandiver?
Well, we're going to talk about force vibration now. How many of you have cell phones on you? And how many of them can vibrate? Do you know why it vibrates? Inside of it, it's got a little motor. And on the motor, it's got a little off-center mass. And when that mass spins around, it's like this. Now, there's tension in the string, right? And so when the string is when the ball's over here, there's a force pulling this way. And when the ball's over here, there's a force pulling that way. The same thing with that little mass going around in your cell phone is it exerts a force on whatever is holding it in place, in this case, your cell phone. So I've got a little DC motor here, and I'll turn this on, and I'll give it some juice, see if I can get it in the field of view here, and slow it down so you can maybe actually see it go around and around. There you are. Come on. Come on. Let's do it. There you go. All right, so there's a giant cell phone motor, right? Okay, so if I take one of these and I mount it on a beam, so this is a kid's toy called a squiggle pen. There's a squiggle pen. Now, in the end of the squiggle pen, there is a rotating mass. It's right in here, and you can see it through there. Can you verify that there's really one in there, right? Okay. And when that thing spins around, it's just like your cell phone. Now, a beam will vibrate. And it has a natural frequency. that's in this case, like you can see there. And if I turn on this squiggle pen, it's going pretty fast, actually, 30 hertz or so. Much, much faster than this beam's natural frequency. So you don't see much vibration. But the beam's natural frequency is a function of its length. And in fact, it goes roughly like 1 over length squared. So as I shorten up, here's the natural frequency when it's quite long. Now if I make it shorter, faster, shorter, faster yet, right? So what will happen if I make the length of this beam so that the natural frequency of the beam is exactly the same as the frequency of the vibrator? You had a guess right there. Yeah, a lot, right? If I get it tuned really carefully, it ought to vibrate a lot. Let's try it out. So out here, it's running now, and it's not vibrating much. And I'm going to put my clamp on it in a second. Okay. Not much. And I'm going to start shortening it. Shorten a lot. Still not much. Now I'm going to move it right to where I know is pretty good.
It's very sensitive.
There we go. I mean, it's...
There we go.
All right. Now we're going to need to dim the lights. And I just happened to have brought along a handy-dandy strobe attack. I'm the director of the Edgerton Center, and Doc Edgerton was known for strobes, right? Okay, so I went upstairs to the Edgerton Center and borrowed a strobe. And now if I... We do want that up there. Yeah, right. Okay, that's looking pretty good.
Maybe if we can dim
dim the lights even
these
further.
Lights is what we really have to have down.
So if I match the the frequency of this strobe to the beam, I ought to be able to stop the motion. You can see the little mass going around on the end of it. I'm getting close. Real close. There it is. Stop motion, okay? And it's saying about 16. All right. All right, now if I detune it again, then it'll start going again. All right. So, but now what if you didn't have...
Let's have lights up a little.
Let's turn the lights back up for a second.
Good.
So now what if you didn't have a strobe attack and you wanted to estimate, you wanted a way of estimating the frequency of this thing? How do you measure the natural frequency without electronics? Well, a little knowledge goes a long way. And I'll give you an equation. I'm going to measure the natural frequency of this with this little piece of steel. But I'm going to give you an equation first. So if you have a cantilever, so it's built in at this end, has length L, has some Young's modulus, E, has a property we know is its area moment of inertia, which is BH cubed over 12. It's just a property of the section. This thing has a rectangular cross-section. This is B, and this is H. So it's just a property of the cross-section, and it has cross-sectional area then equal to BH. I can tell you that the natural frequency of this simple beam, I can give you a formula for it. And that is omega n equals 1.194 squared, just a number, times pi squared over 4L squared square root EI over rho A. And rho is the mass per unit length. So rho A, mass per unit volume. Sorry about that. When you multiply the cross-section area, you get mass per unit length. E is just a property of the material. That's a property of the beam. This is a property of the beam. This is just a constant. All of that's a constant. If I figure this all out, I will come down to a number that is 3.706 divided by L squared for a steel beam of these dimensions. It's 30 thousandths of an inch thick and about half an inch wide over L squared. So now, if all I have to do is determine the frequency that thing's vibrating at, measure the length of this little beam, and calculate it, and I'll know what the frequency is. Let's try it out.
So it's like a ruler.
Yeah, it is. It's like it's a frequency ruler. And in fact, in the old days, before lots of electronics, people had these things just marked out in hertz. So now, if I set this out here, change the length of this until it vibrates like crazy. When it's vibrating like crazy, I'm on the right length. So it's pretty long right now. I'm going to start making it shorter. Vibrating a little bit. Can you see it up there? Yeah, and we could dim the lights a bit. It'll help again. All right, it's vibrating a little bit more. That's beginning to vibrate a lot.
You can't.
And hey, we need the we need our strobe
here. Yeah.
Takes it a minute to wake up. There we go.
Okay, so
pretty close.
Yeah.
And now let's aim it down on there. Okay. Okay, you see that little guy moving up down some, but not. Let's see if I can get it to move it up and down a lot. Oh, there it goes.
Whoa.
Okay.
Do you bend spoons too?
Oh, there we go. It'll go like crazy now. All right. So I'm pretty close, right? Look at that. Okay. So if I measure, the length of my little beam, and stick it in the formula, I will have the frequency that this thing's vibrating at. And it turns out to be the strobe's mark. Actually, the strobe also has a readout. I can read on the dial. It says 1,940 RPM. Turns out to be about 32 hertz. And when you do this calculation, it's 13.5 centimeters long. You get 1,942 RPM, that's pretty close. 2 parts in 2,000. Okay, so this is a simple little calibrated, or you can calibrate it, ruler for measuring frequency.
So if you had the strobe going only half as fast as the period there, how do you know it would still?
Yeah. So if that thing's going round and round and you're flashing the flash once every cycle, that's what we're doing. You're catching it in its motion to the same place every time, right? Now, if I only flash the lamp every other time, so I go flash and I catch it here and it goes around once and around twice and it goes flash again, I catch it every other time, it looks the same, still stop motion. But what if I flash it twice for every cycle? What'll happen? Catch it at the bottom of the top. And that's how, with the strobe attack, you determine you've got the right one. You get it at 1900 RPM and you say, I think it's right, but you double it. You put it up at 3800 and see what it looks like. And in this case, you see it up here and then down there.
You get a double image.
You get a double image.
So we've talked about what happens when you have a constant system with omega n as the natural frequency, and we vary the input to it, and we get these response curves that say that when you're near that resonant frequency, the gain goes up. Here what's happening is a little bit different because the frequency of the input is the frequency of the pen. That's constant. And what we're doing now is varying the natural frequency of the little ruler system. But still, when the two get to be close together, when omega is about omega n, that's when you get this resonant peak, and that's what we're seeing in this system.
All right.
So thank you. Your research involves vibrations and things also, doesn't it?
Absolutely. Let me draw one little diagram for you. I study structures in the ocean.
We're going to switch over to the
and while I'm doing that, we can set up the, yeah. So imagine you have a cylinder. And that cylinder, and I'm going to show you a movie. The cylinder is, in fact, 3 feet long. And it's about 3 inches in diameter. And it's mounted on springs. And it can move up and down. Now, if in this situation you have a flow, air or water, in this case I'm going to show you water, flowing past a cylinder, in the wake of the cylinder, vortices are shed, little eddies. And the frequency of the vortex shedding is approximately 0.2 times the flow velocity divided by the diameter in any consistent set of units. So I study big things in the ocean. If you're drilling for oil, it's through a thing about 1 meter in diameter. So if D is a 1 meter, in 1 meter per second is a common flow velocity of currents in the ocean, about 2 knots. So 1 over 1, so it's about 0.2 hertz. So something this big around with a current of 1 meter per second going by it will have vortices shed at 0.2 hertz. And every time this vortex is shed, you get a force upwards, and it's on the other half cycle, you get a force downwards. It causes a periodic force on the cylinder transverse to the flow. The flow's coming like this, the force is this way. And if that force is near a natural frequency of that string, what'll happen? It will oscillate. So we're going to show you an example of that. A friend of mine at the University of Michigan is interested in ways in which you can extract power from the flow of a river. Rivers are hard to get power out of unless you have Grand Coulee Dam and a 300-foot drop. But if you just got water coming by at 1 meter per second, it's hard to get energy out of it. But he's figured out a way to do it. So he's got an experiment we're going to show you where this thing is 3 feet long, and there's 4 of them in a row, actually. And they're excited by these vortices coming off the cylinder. And instead of a dash pot, instead of just an ordinary damper, the damper is the generator that's hooked to it. Generator sucks power out of it and acts like a damper in the system.
Instead of just heating up the damper, it's doing something better.
It's actually sending electricity down the wires. Okay, but it's taking energy out of the system. The equation of motion is exactly the same. It's that same oscillator equation that we started with today. So we're going to show you a movie of this thing in action. The flow velocity, 1.3 meters per second.
Ready?
Yep. 2.6 knots. This was very recent, January 31st. So these are these 3-foot-long cylinders. You kind of have an almost oblique end view. These are going up and down 3 or 4 diameters.
So I see the cylinders behind these rods.
Right. The rods are the struts that hold the cylinders in place, and the struts are mounted up where the springs are up above where you can't see them. So in order to confine these cylinders so that they'll only go vertically, they have struts attached to each end that are in guides that let them go up and down.
Wouldn't want to be underneath one of those things.
No.
They look like they have a lot of power.
Yeah, it looks like you could chop carrots or something in there, right?
I was thinking of stamping wine. But
Yeah, stamping wine? Okay, yeah, I can do that too. All right. So vibration can be good.
Lights up.
All right, thanks a lot.
Thank you very much, Professor Vandiver.
And if I see you in September and say, remember that equation, I want you to remember for me. Okay.